The Embraer jets are equipped with an X-band digital radar receiver transmitter that is designed for weather detection and ground mapping. A flat-plate antenna equipping the system uses an 18-inch plate, 24 inches on the optional 880 system, and produces a 4.2-degree beam. The system range is adjusted to 6 different distances between 10 and 300 nautical miles, and a target alert option is available when severe weather outside of the selected range is detected. The WX menu controls all the radar operating modes and gain functions. The word radar stands for radio detection and ranging, and the device is based on the fact that some energy of the radio waves are reflected by the objects they strike. Radar energy transmitted is returned and provides display reading. The weather radar is a water detector. That is, it can detect water in its liquid form. Weather radar detects droplets of precipitation size. Strength of the radar return, echo, depends on drop size and number. The greater the number of drops, the stronger is the echo. And the larger the drops, the stronger is the echo. Drop size determines echo intensity to a much greater extent than does drop number. Fog or shallow cloud formation will be ignored by the weather radar. The energy is simply absorbed and no return is provided. Frozen water, cirrus clouds, small hail, and snow are crystalline, so the pilot will see no return at all. When the system is in the weather detection mode, storm intensity levels are displayed in 4 bright colors on a black background as shown. Areas of very heavy rainfall are displayed in magenta, heavy rainfall in red, less severe rainfall in yellow, moderate rainfall in green, and little or no rainfall in black background. You can also understand these levels as a turbulence probability indication. For example, green level has no chance of containing severe or extreme turbulence, but has from 5 to 20% chance to contain moderate turbulence. Potentially hazardous turbulence is present in all thunderstorms, and a severe thunderstorm can destroy an aircraft. Strongest turbulence within the cloud occurs with shear between updrafts and downdrafts. Outside the cloud, shear turbulence has been encountered several thousand feet above and 20 miles laterally from a severe storm. A low-level turbulence area is the shear zone associated with a gust front. Often, a roll cloud on the leading edge of a storm marks the top of the eddies in this shear, and it signifies an extremely turbulent zone. Gust fronts often move far ahead, up to 15 miles, of associated precipitation. The gust front causes a rapid and sometimes drastic change in surface wind ahead of an approaching storm. Weather or terrain is selected in the Map menu. In the Weather menu, you will find buttons to control radar weather and ground mapping. Selecting Radar Weather, WX, the system is in Weather fully operational mode, and WX is displayed in the Mode field. Selecting GMAP, the system is in ground mapping mode, and GMAP is displayed. GMAP is active only when airborne, but may be armed on the ground. When clicking Standby, the system is placed in standby. The antenna scan stops in the tilted up position. The transmitter is inhibited, the display memory is erased, and standby is displayed if the aircraft is airborne. The system is in forced standby mode when on the ground to eliminate the X-band microwave radiation hazard. Forced standby will appear. Overriding the forced standby mode requires both pilots to select the appropriate button on the weather controller. Checking the sector box, the sweep changes from the normal plus or minus 60 degrees, 12 sweeps per minute, to plus or minus 30 degrees, 24 sweeps per minute. When the stabilization off box is checked, attitude stabilization is off. The purpose of the stabilization system is to hold the elevation of the antenna beam relative to the Earth's surface, constant at all azimuths, regardless of aircraft bank and pitch maneuvers. The stabilization system uses the aircraft attitude source as a reference. When the variable gain box is not checked, the system is at the normal preset gain recommended for weather avoidance. When the box is checked, the system is in variable gain, and the gain box enunciates a green digital value that is adjusted using the outer concentric knobs on the CCD. Variable gain is useful for additional weather analysis and for ground mapping. In WX mode, variable gain can increase receiver sensitivity over the calibrated level to show very weak targets, or it can be reduced below the calibrated level to eliminate weak returns. When the target box is checked, the target alert mode is on, and TGT is displayed in the mode field. Target alert is selectable only in the weather mode and is not available in the 300-mile range. The system monitors beyond the selected range and 7.5 degrees on each side of the aircraft heading. If a return with target alert characteristics, red or magenta, is detected in the monitored area, the target alert annunciator changes from the green armed condition to the amber alert condition, which advises the pilot of potential hazardous targets directly in front of the aircraft that are outside the selected range. When an amber alert is received, the pilot must select longer ranges to view the questionable target. Selecting target alert forces the system to preset gain. The rain echo attenuation compensation technique compensates for attenuation of the radar signal as it passes through rainfall. As the radar energy travels through rainfall, the raindrops reflect a portion of the energy back toward the airplane. This results in less energy being available to detect raindrops at greater ranges. This process continues throughout the depth of the storm, resulting in a phenomenon known as attenuation. Storms with high rainfall rates can totally attenuate the radar energy, making it impossible to see a second cell hidden behind the first cell. Strong targets, high attenuation levels, cause the receiver to reach its maximum gain value at a short time, short range. Weak or no targets, low attenuation levels, cause the receiver to reach its maximum gain value in a longer time, longer range. Once the receiver reaches its maximum gain value, weather targets can no longer be calibrated. The point where red level weather target calibration is no longer possible is highlighted by changing the background field from black to cyan. Any target detected in the cyan field is not calibrated and must be considered dangerous. All targets in the cyan field are displayed as magenta fourth level precipitation. When the turbulence box is checked, the turbulence detection mode is active. This mode is only available on the Primus 880 system radars and is available only when the system is in the radar mode and the range is 50 nautical miles or less. Areas of moderate, severe, or extreme turbulence are displayed in soft white. When the turbulence detection mode is selected, a T is added to the WX enunciation. It cannot detect clear air turbulence. The map and weather range may be controlled by the CCD outer knob when the map page is displayed. The MFD is selected on the CCD, and the knob prompt is displayed at the range value. Range selections are 10, 25, 50, 100, 200, and 300 nautical miles. The MFD indication in the inner range ring is the half range of the selected value. Selecting the range over 300 nautical miles will show an overrange message. Radar does not detect storm in the overrange area. Manual tilt is controlled by the CCD inner knob when in map page. The tilt knob selects the tilt angle of the antenna beam relative to the horizon. The radar beam literally slices out a horizontal cross-section of the storm and displays it as the viewer was looking at it from above. The height of the slice selected for display depends upon the altitude and also upon the upward or downward tilt adjustment made to the antenna. Check the relationship between tilt angle, altitude, and selected range. Observe the distance above and below aircraft altitude that is illuminated by the antenna during level flight with 0-degree tilt. The range at which ground targets can be observed is affected by the curvature of the Earth, the distance from the aircraft to the horizon, and altitude above the ground. As the tilt control is rotated downward, ground targets first appear on the display at less than maximum range. To find the ideal tilt angle after the aircraft is airborne, adjust the tilt control so that ground clutter does not interfere with viewing of weather targets. Usually, this can be done by tilting the antenna downward until ground targets begin to appear at the displayed periphery. Ground returns can be distinguished from strong storm cells by watching for closer ground targets. The more the downward tilt, the closer the ground targets that are displayed. When the ground targets are displayed, move the tilt angle upward until the ground targets begin to disappear. Proper tilt adjustment is a pilot's judgment, but typically the best tilt angle lies where ground targets are barely visible or just off the radar image. The tables shown give the approximate tilt settings required for different altitudes and ranges. If the altitude changes or a different range is selected, adjust the tilt control as required to minimize ground returns. Proper tilt management is very important for a correct weather picture. Flight level 200 defines the freezing altitude. Water in its liquid form is less likely above this level. There may be water occasionally at higher altitudes, especially where there is heavy convective activity, though. If, above the freezing altitude, the radar is adjusted to capture weather buildups ahead of the aircraft, probably little or no return will be shown on the radar display. Therefore, do not tilt radar beam towards the top of the buildups, because this portion is a frozen area, consisting of hail, snow, and cirrus clouds. Tilt radar to the middle of the cloud formation. Tilt should be changed as flight proceeds. If it is not changed, the thunderstorm appears to weaken as the aircraft approaches it. In addition, dangerous thunderstorms can develop in only 10 minutes under the radar beam as the aircraft approaches. After heading changes, the pilot should adjust tilt to see what was brought into the aircraft flight path. Remember, the upper levels of convective storms are the most dangerous because of the probability of violent wind shears and large hail. At low altitude, the tilt should be set as low as possible to get ground returns at the periphery only, as shown. The pilot must make adjustments for the effects of mountainous terrain. However, tilt upwards regularly to avoid flying under thunderstorms. After takeoff, upward tilt is required to avoid ground returns as well. During climb, the tilt technique of slightly painting ground returns is applicable. Select negative tilt and adjust it regularly as altitude changes. When the altitude compensated tilt act box is checked, the system automatically tilts in relation to the current altitude and currently selected range. Tilt is automatically adjusted to show a few ground targets at the edge of the display. It is best suited for the altitude operation in weather surveillance mode. In altitude compensated mode, the range can be normally changed. The tilt control can fine-tune tilt setting up to 2 degrees. When active, an A is added to the tilt readout. Operating at high altitude terrain can result in lower than desired tilt angle. Using manual tilt is recommended in this case.